Hi guys, welcome back to the channel. We'll be continuing our discussion about file I/O. In the last video, we talked about kernel and user space and then moved on to understanding the buffering that kernel offers, both in the kernel space with kernel buffering and buffering offered by the standard I/O library in the user space. For today's video, we are going to understand the file system. We'll talk about the inode table, what all information it holds, and how are files stored on the disk. We'll talk about file attributes, and file permission is one major attribute that we are going to talk about. We'll also talk about sticky and set user ID permission bit. So let's get started on this one. File system is a way of organizing files and directories on the computer. Since there can be multiple techniques of organizing files, there are multiple file systems that exist today. Linux also supports multiple file systems like ext2, HFS, FAT file system that was developed by Microsoft. Each disk is divided into multiple partitions. On Windows, we usually divide it into C, D, and E partitions, and each partition in turn can run a file system. So I can run a ext2 file system on this partition and HFS file system on this partition. Each file system has these information. The first information it holds is in the form of a boot block. This has nothing to do with the files this file system holds. It is used by the OS during the boot up process. Super block is the next set of information that file system holds, and this contains information about how big is the inode table. Inode table is the actual table that holds the file. It contains multiple rows where each row corresponds to a file or a directory. ls-li is the command that we use to print the inode entry for a particular file or a directory. Here I have printed the inode entry for this directory, but this could have been a file as well. The big number that you see in the first column is the inode number. This is basically the row number where this entry is being stored. Next is the permission bits associated with this directory. A D as the first permission bit dictates that this is a directory, whereas a empty permission bit dictates that this is a file. It then lists down all the permissions for the user, group, and other. It lists the UID and the GID, that is the owner's user ID and the group ID. This is the size of the file, the timestamps, and in this case, since this was a directory, at the end it is listing all the files that this directory had. Other than these columns, each row in the inode table also contains the pointers to data blocks. This is the region where the file is actually stored. Let's dig deep into the inode table and understand how the data pointers are stored, it will also be important to note that such a technique of storing the pointers to the data block in the inode table allows us to store the file in non-contiguous blocks. Let's see the inode table and understand this in detail. Here I have added an enlarged view of one inode entry. These are the initial attributes that tells us about the size, permissions, type, timestamps that are stored in this block. Although in this slide we are going to talk about the data block pointers. For file system ext2, there are 15 block pointers. Before we dive into understanding how block pointers work, there are few important few important things that we have to keep in mind. For a 32-bit system, the pointer size is 4 bytes, and the optimal physical page size that has been chosen for 32-bit system is 1024 bytes. Similarly, for a 64-bit system, the pointer size is 8 byte and 4096 bytes is the size of the optimal physical page size. Physical page size is equal to the virtual page size as well, and the translation between virtual page to physical page happens through a memory management unit. We can talk about memory management unit, address translation, and paging in some other video. But to understand the block pointers, let's keep in mind the page size of 1024 for a 32-bit system and 4096 for a 64-bit system. This physical page is the actual placeholder of data. Any data that we write is stored in these physical pages. Each block pointer between 0 to 10 directly points to a data block that is equivalent to the page size. In other words, each pointer here is pointing to the first address of a physical page. Since there are 10 pointers, there is 10 into 4096 bytes that we can store using these 10 block pointers. This is for a 64-bit system, and for a 32-bit system, it will store 10 into 1024 bytes. The 12th pointer is an indirect pointer that points to a block of pointer. What I mean by this is the 12th pointer will point to a physical page of 1024 bytes in context of 32-bit system, and it will contain 1024 divided by 4, 256 pointers on this physical page. This is because size of a pointer on a 1024 page size is 4 bytes, and with this calculation we get 256 pointers on this physical page. Each pointer on this physical page would point to a 1024 size physical page, which actually contains the content of the file. So with such indirection, we'll be able to store 256 into 1024 bytes of data. 256 is the number of pointers that we have on this physical page, and each pointer in turn is able to point to a 1024 sized page. That is why we are able to store this many bytes using the 12th indirect pointer. The 13th pointer is a double indirect pointer. The 13th pointer in inode entry is a double indirect pointer where it points to a physical block containing 256 double pointer. Each pointer points to a memory location of another block which in turn contains 256 pointer, and this block and each pointer in this block actually points to a physical page that contains the contents of the file. Let's see how many bytes we can store with this indirection. 256 is the number of pointers that we can store on this page. 256 is again the number of pointers that we can store on this page, and the last physical page is of 1024 bytes. We can store an enormous size of file with this double indirect pointer. For a file size even greater than this, we have a triple indirection pointer at the 15th location of the inode entry. The size of the file that we can store with such indirection is close to 4 TB. Coming back to our original slide on file system, we now know that the disk is divided into multiple partitions, where each partition consists of a file system containing boot block for booting purposes, super block that contains information about the size of the inode table, and this also contains the information about size of a data block. For 32-bit, it is usually 1024 as we already discussed, and for 64, this is 4096 that has been optimally chosen. We already talked about inode table, and to remember the contents of inode table, it's always easy to remember the fields that we see when we run a ls-l command. Adding a -i in ls command prints the inode number as well. This is the row number of the inode entry as we already discussed, and all the other fields are also populated in this inode row. Data blocks, as we already discussed, is the actual place where we store the file. It is also possible to retrieve all the attributes that we see in ls-li command for a file in a program as well using a stat function call. This is a function that is defined in stat.h, and we have to pass the name of the file that we are trying to stat and memory location of this structure type. This structure has been expanded here, and it shows all the fields that this structure contains. These fields correspond mostly to what you see when you run a ls-li command. It has the inode number, the file type and file permission, user ID, group ID of the file owner, file size, timestamps, and it also tells you what is the optimal block size for I/O. This is usually 1024 or 4096 depending upon 32-bit or 64-bit system. These are the permission bits that we often see when we run a ls-l on any file. The output is divided into three parts. The first three fields represent the user permission. The next three are the group permissions, and the last are the permission for other users. A read and write permission is represented by R and W respectively, and a X represents an execute permission. There are these three permissions as well that are called set user ID, set group ID, and sticky permission bit. Set user ID bit allows the program to assume permissions as per the owner of the file. To explain this better, let's look at an example where a user Nishant creates a file called virus.c and some other user Arun executes this program. If set user ID bit is not set, then the effective user ID of this program would be that of Arun. But if the set user ID bit is set on this program, then the effective user ID of this program becomes Nishant. So the program has picked up the user ID of the actual owner who created this program. Same analogy applies to set group ID as well, where the process takes the group ID of the owner of the file. These bits have to be handled very carefully, otherwise a program written by the root user can be run by some other user XYZ, and this program can take the effective user ID of root and have enhanced privileges on the system. For any malicious and bad programs, this can be disastrous for the system. A sticky user ID, if a sticky permission bit has been set on a file, say xyz.txt, then this file would be avoided to be moved out of RAM into the disk into the swap space. It sticks in the RAM so that the running program has immediate access to this file and is never swapped out onto the disk.